operate with this. We also have some commercial robots, robotic arm and robot dog. Again, you'll see them a little later. So that's the setup, that's the stage. I feel like a roboticist who wants to build better robots. And when I say that, then I think of closed loop systems like this one, where we have some motors. Here we have two different types of motors on this video. We have the wheels and we have a robotic arm that coordinates activity. And here the task for this robot is to detect an outlier in this line of blinking poles. And once the outlier is found, approach it, grab it, and place it at the right position. That's a pretty complex task that any one of us could program in a couple of lines of C code, because we know exactly what to do. But here we use spiking networks to coordinate wheels and robot arm and robot motion. And the real challenge is to get these three aspects working together that you see on the top left. There's always an algorithm on top. This could be a spiking neural network. This could be some procedural code. This algorithm has to efficiently execute on some piece of hardware. And that hardware then connects to a physical system consisting of sensors and actuators. There are very early examples of this. So this is work 10 years or older, where we've done crazy things like adding Spinnaker computing boards, connecting them directly to sensors. There's an interface board on the top left. Or we've even mounted Spinnaker PCBs on mobile robots so that we have local computation. We have a mobile neural network, and we've done simple tasks like optic flow computation on the bottom left so that the robot can center itself in the hallway. Or we had stereo vision where we simply detected a blinking light, and based on disparity, the robot kept distance to that blinking light. Very simple tasks, very early exploration of how to use spiking neurons embedded on board of robots. I don't think these robots were outperforming any other robots at any point in time, but there were initial examples of spiking systems embedded on a robot. And in a way, that's still what we do. So in my lab, I'm very curious, very interested in event-based neuromorphic vision. And the second bold aspect here, real-time computing and control in event-driven or spiking neural networks. That's the main research directions on all of these different robots shown at the bottom. So I don't need to reintroduce you to event cameras, but here is the main idea of what is different in our event cameras. You can go out and buy event cameras from a number of different vendors. The most obvious sources are Prophecy and Innovation, Synsense now. Whenever you buy these cameras, you get a little camera box with a USB cable that connects to your computer. You can record data, you can run live or real-time processing algorithms on your computer. That's what people do. And then they assess energy consumption, they assess latency and so on, which is always dominated by, let's say, an FPGA or some electronics inside the camera module that creates USB packets, and dominated by your computer and the USB latencies, the operating system latencies, all the overhead that is not intrinsic in event camera data. So what we've done in the lab for some years by now is develop embedded systems where we connect, there's a laser pointer here, right? Where we connect camera chips directly to computing units. Here's a microcontroller as an example, but we have other computing units. So this camera chip immediately talks on a data bus to that microcontroller. Here's a smaller version on top, so that we avoid the energy overhead in producing digital communication signals, and we avoid the overhead in processing time for the operating system to handle USB packets and task scheduling and so on. So we can run bare metal algorithms on this device, either in standard C or in some higher level neural network description that then maps to microcontroller code, or even use dedicated neuromorphic processors here. What do we do with these computing units? Well, we put them on small robots. That's the whole idea. So here's a small chain of a very small robotic device. First one is remote controlled by the student sitting somewhere in this room. The other two robots simply follow the ones in front because of a blinking light on top. So it's not the world's most complicated task, but here we have a vision scenario where robots can detect their leaders based on a 500 Hertz blinking light. which is extremely easy to spot in the stream of incoming events, so that the following robots can just follow. And that's, of course, an example for robotic systems that could work in manufacturing environments or be used for docking simulations and so on. Second example on the top right is a very early version of a robot mapping with event cameras. So here we have a little robot driving around in our arena. This is speed up by a factor of 4, I think. But the point is that there's only a single event camera looking up at the ceiling. It's a very simplified process with a fixed distance to the stimulus, bottom to ceiling. And we've added some pattern to the ceiling, but this event camera observes the pattern on the ceiling by moving, produces events which then serve to build a map and to perform localization on that map simultaneously. So there's a SLAM process of simultaneous localization and mapping, which is happening on board of the robot, which is in fact happening in that little microcontroller on the robot here. So we can build a representation of what the robot sees in 2D on board of a microcontroller. So it's a very energy efficient system. And now to get Guido interested again, we also have drones. So we add similar setup on small drones. And I'll have a slide for these drones coming up somewhere soon. So here's an explanation of how to find events in the event stream. But that's a super simple algorithm to process incoming events. I don't think we need to go into this much more. It's very old work. And I've already explained that these robots simply follow one another by detecting the blinking light on top. This is another very old work where we monitor a moving object, here the pan on a little cart that moves left, right. And as soon as the pan begins moving, we're getting events in. These events tell us where the pan is. So here is a representation of where and how the pan moves. All these events cause incoming stimuli, and each of these events gives us some information about where that pan is in terms of orientation and position. And combined, we can use a Huff transform, an event-based Huff transform, to extract the most likely position of the pan in terms of its slope and its base. Again, it's very old work that captures these ideas of element-wise, one-by-one event-based processing of incoming spikes that allow us to understand what's happening in the world. Here we have this example with drones, where we have embedded very small versions of these event cameras on board of a very small drone. So this is some 8 by 8 centimeters, where we can run algorithms to track lines on board inside the microcontrollers. And once we have multiple of these event cameras looking at different directions, and we have objects moving, so tracking lines in the environment, we can use that to infer ego motion in the scene. If we do it like this on a drone, we can also further miniaturize that and get really, really, really small drones in the world. And this is work in progress, where we see this is a miniaturized drone on my fingertips. It's only 25 by 25 or 23 by 23 millimeters in size. And now when we talk about applications of neuromorphic, where neuromorphic really leaves an impact, I think this is an interesting domain in between large computation and in between extremely tiny computation, where the energy requirement or the energy budget that we have is well matched with the energy requirements of the computing system. So let me say this again. Here we have a mini drone. This mini drone has a tiny battery. The motors of this mini drone together draw about 300 milliwatts in operation. If I add my Intel Loihi chip onto that, or if I add my the GPU-based Jetson or something like that, then of course the power consumption is a disaster, because then my vision process takes so much more power compared to my actuators. On the other hand, I don't need to go to milliwatt or microwatt power consumption, because these motors draw 300, 400 milliwatts anyways. If I add 10 or 50 milliwatts, that's acceptable. I don't need to go to microwatt setting. So here I have enough flexibility with my processing algorithms on board of a microcontroller and a tiny event camera embedded in here, so that we can add computer vision onto the mini drones and have that operating for reasonable amounts of time without with vision input. This is work in progress, so maybe next year, maybe for the summer school that has been advertised earlier, we can show this working. Let's pick up some other projects where we use event vision and event-driven computation. Here is an example where we have human interacting with robots. So there's a human robot co-workspace with a person interacting with this robotic arm. And we have multiple event cameras observing the robotic workspace. We assume there's a human worker either working with tools or working with heavy objects, so the robot arms need to support or interact with a human user. Here we have a very simple approach by training a spiking and convolutional spiking neural network to detect objects, for example, a hammer or a wrench. We created some labeled training data set to track objects. And once trained, the spiking neural network will give as output the position of the tool. And if we have 3 cameras, we have 3 times the position of the tool. So we can convert this into a 3D position of the device, of the different tools that are possible. We have relatively small neural networks so that we can run the networks in real time on GPUs. And here is an example video of one of my students interacting with the robots, bringing in a hammer, and the event cameras will tell us where that hammer is so that the robot can follow and put a nail at the proper place. It's a very simple demo where spiking input will provide an XYZ and eventually a pose, a 6-dimensional pose for human-robot interaction. We plan to do this with extreme low latency, and of course, event cameras are low latency devices. The spiking networks in principle are extremely low latency devices, but here we had several layers, and each layer needed to build up information. So because they are leaky integrators, they're not immediately forwarding information. So we need to wait a little while. So in the end, it turns out we did get a rather long latency of tens of milliseconds, which is why the robot is so slow. So if we argue that we really want effortless, we want very smart, very fast human-robot interaction, we also need to rethink our spiking neural network processing systems. Here's another example where we go back to microcontrollers. This is a sensing project. There's no robot involved here. We would like to observe traffic in cities. And today, traffic is usually very chaotic. There are many different participants. We would like traffic to look like this. We would like to have happy people on bicycles and scooters and whatnot. So we have a project together with the city of Stockholm where we want to observe traffic participants, observing privacy rules and then running in real time at the sensor level. And they say, of course, we could do that. We could use cameras everywhere in the city and add computing units at these cameras. But that's very costly in terms of energy. You need a relatively big computer in all of these sensors. And it's questionable about privacy. So what we offered is using event cameras only and identify very simple information saying there is a car, there is a bicycle, it's going roughly this direction. It's a very simple project where we record test data sets simultaneously with event cameras and regular cameras initially. So we get some recordings where we have cars driving, and we can use standard technology, standard YOLO algorithms to label, and we have simultaneous event camera recordings. So we have a large data set like that, and simply train our spiking neural network based on the labels obtained from a computer vision setup. So again, we have labeled data. We can transfer these labels into the spiking data set, and based on these labels, ask for a blob of activity saying, here is a car. That's an extreme simple example here where we basically have cars and some small distractors like pedestrians or bicycles. It also works in more complex settings. Here you see that after training, if our spiking network only gets spiking input, then the spiking network can produce an output that shows the location of activity where we have traffic participants. And we can implement this spiking network, again, either on our microcontroller, where we have a few tens of milliwatts of power budget, or we can decide to go to specific neuromorphic hardware, but it's definitely orders of magnitude more power efficient than traditional computer vision tracking. Here's another one example of high-speed closed-loop systems where we built an air hockey game. So it's a children's game. So it's a tabletop version of the air hockey game where this puck is very, very fast. There's a human player with his pedal, and we built a robot player playing against the human. It's an extremely simple setup with an event camera observing top-down, and then we feed the event data into a spiking neural network, either running on a GPU or running on Spinnaker. I'll jump ahead and give you the result video right here and then tell you the exciting part afterwards. This is how the game plays by just tracking the puck and mimicking the puck position, so duplicating the vertical position, so thereby defending its own goal. It's so fast and so efficient that you cannot, as a human, cannot beat the game. So if you ever want to lose a game of air hockey, you're welcome to come by and play against our very simple robot setup. It will only win when it's fast enough. That's pretty obvious. If it's too slow, it can't win. And fast enough here was challenging because we first implemented our spiking neural network on a very fancy GPU card, 5090, very modern, best thing you can typically buy. There was brute force computing power in that 5090 available, and the network itself computed really, really fast. There was no problem to track the puck. What was a problem was the big delay that we faced from getting the data from the event camera, preparing it in some piece of software for the GPU card, loading it onto the GPU card. Then we do the immediate magic computation. Then we have to wait for synchronization, read out again, convert it to a motor signal, and send it to the motor. So there's a lot of delay, there's a lot of overhead in this closed loop system, and that's critical for robotics. So the only reason why we got this to work really, really fast is because we have connected our Spinnaker machine directly to the event cameras. So there's a no computer microcontroller / FPGA interface from event camera into Spinnaker. Then we run our tracking algorithm on Spinnaker, which is about 10 times slower than on the GPU. But the Spinnaker output, again, was immediately sent back to the motors. So we avoided all the overhead. So it's the overall system latency that is really, really critical for many of these robotic applications. It's not the elementary computing power. But here this is working, and still we have not managed to get it working on a GPU today. Not fast enough. Here's one more quick example, and then I'm almost done to wrap up. I'm sure you've seen these Unitree robot dogs a lot in the last few days. They're here everywhere. We have a Unitree, one of the very old in our lab. This the robot walking around in our lab, and you see it's not walking like real dogs walk. You see it's still walking like this all the time, still like shaking and juggling. And if you look at the onboard camera signal, so they have built-in cameras. If you extract that camera signal, it looks a lot like this. So there's a real problem for any computer vision. We've added event cameras to our little robot dog, and we get a stereo event stream from that robot dog. And here it also looks blurred because we recreate a video, and we use a very simple way to recreate this video. But in principle, you understand the idea of event cameras. There's crystal clear event over time patterns, and we're in the process of designing algorithms to work on board of that little robot. And if you look carefully, you see there's an extra computer on our little robot dog here. So like here we added an extra computer, so we want to run spiking event-based algorithm stereo detection on board of that robot. This was really a number of examples, all hovering around this idea of using neuromorphic computing, understanding neural principles of how they compute so that we can implement them in neural computation on real robotic systems. And I think the punchline here for today is, number one, I think we need to reduce overall latency. And number two is, I think we are good in brute force computing power. We have enough ideas from standard computer vision about how to process events or frames or reconstruct frames from events. I think we need to spend more time thinking of elementary event computing, of understanding, of designing algorithms that operate on event by event base or very, very small bags of events and create an ever increasing understanding of what's happening in the world. And my approach to this is using embedded event-based processing, using these event cameras combined with small computers, microcontrollers or similar, so that we can get faster closed loop systems. Thank you very much for the attention.
Thank you very much, Jörg. It's really nice to see so many different robots and applications controlled with spiking networks and using event cameras. So we'll open up for a few questions for Jörg before we do the panel.
Thank you. Yes, thank you, Professor, for your wonderful talk. Yeah, I also have many questions, but just one question. So, you have done many fantastic work on brain-spine SLAM navigation. Yeah, based on neuromorphic chip. Yeah, previously several years ago. Yeah, so my question is, how can we build more energy efficient and adaptive navigation system for micro robots like the micro draw? Yeah, by mimicking the neural circuits or hippocampus in Tokina, the navigation, region. So, thank you for your. Could you share some insights or suggestion on this topic? Yes,
yeah, thank you. Thank you very much for the question. I think it's a very hard question to answer. For at least the following reason, navigation is a high-level process, right? It's a very complicated aspect to solve, and it's very unclear to me how spiking systems or event-driven systems are beneficial in the context of a larger, global, longer timescale problem.
Yeah.
That's why I focus on sensory pre-processing and on early stages of signal processing. And I think that's where neuromorphic can bring biggest advantages and provide most energy savings. If we have an abstract signal, so navigation only needs to happen at a few hertz, if at all, in most systems. So I think then our traditional, let's say, mathematical understanding of how to optimize navigation is very good.
Thank you.
Thank you for your very inspiring talk, Jörg. And I'm just wondering one quite general question. So in embodied AI, what kind of role the neuromorphic chip should play in this kind of area? So I wonder in future, if we try to build a whole sensory system for a robot, do you think how the chip should be like the future improvement on the neuromorphic chip?
There's also that's a very good but also very open-ended question. I think we're mainly missing an algorithm understanding of what we want to do in an efficient, event-driven way. And once we develop our algorithmic understanding, then we can decide or discuss what and how we can map this onto chips, or how we need to change chips. I'm very happy to see different approaches. There's SynSense, there's BrainChip, there is Inaterra. Different companies offer different solutions, hardware solutions, to implement small neural networks. But what exactly the characteristics are, we just don't know today, because we're still missing an understanding of how to build efficient, small spiking networks. The community is very good in building larger systems, but that's what comes in. I'm leaning out of the window quite far now, but that's many people come in with a computer vision background, and computer vision is all about big models, very large processing power, and that mindset has entered neuromorphic as well, where people keep saying, oh, let's build bigger networks and then we get better, but that does not hit the sweet spot where neuromorphic can thrive, and that's where we need to work. Then once we solve this, once we crack it, then we can go and decide the correct chips.
Okay, one last quick question for Jörg.
Sure.
Super stupid. No, but yeah, let's pay for that.
Thanks for the talk. I have one small questions. So for the community, for the city size, they said the data are more important than algorithm. So, what's your suggestions about collecting more data? Do you think it's important, or if it's important, what is your opinion? Collecting more data, like neuromorphic data, to scale up the whole processing of SL. Thank you.
Thank you for the question. So I'll put up a provocative answer first, and then I'll soften down a bit. So my first answer is don't do that. Do not collect more data. Spend more time thinking. Because training neural networks, training spiking networks is one way to solve tasks. It's a very popular way these days. I fully understand that. And then I appreciate that ANNs are amazing today. But this comes for a big price. And that big price is computation, data source, and so on. Yes, if you have more data, you can do better. But it also means you need to spend more power, more energy, and less cleverness into your system. But that is exactly what I think neuromorphic should do instead. Our brains, of course, we use data, of course, we learn, but there's also a lot of pre-coding, there's a lot of clever design in our brains that makes them very good. And I think this community should spend more energy and more dedication to design smart systems rather than have a different type of learning system, press the learning button, and then we use giant data